Good morning, students. Today we are going to start a new chapter, chapter 6, and the chapter 6 is your electromagnetic induction. Now, the topic which you are going to discuss in this chapter is the first topic is your what is electromagnetic induction. Now, most of you know what is induction, and that part we are going to use it here. So, let me read out what we have written. The phenomenon of producing induced EMF and hence induced current in a closed electric circuit due to the change in magnetic field or change in magnetic flux linked with the closed circuit is known as electromagnetic induction. So you see few parts are here in the statement. One is your closed electric circuit, and another one is your the variation of the magnetic field or magnetic flux. So these two part is very important. So more we are going to explain in our next topic, that is your Faraday's experiment. So in this experiment, you see you do have a coil and a galvanometer. G is your galvanometer, and this is your closed circuit. Now you do have a bar magnet. Now pointing north pole towards the coil, what we are doing, we are moving the north pole towards or away from the coil. Now when you move north pole towards the coil, then the field lines crowded near the coil, and when we take the north pole away from the coil, then the number of field lines interacting with the coil decreases. So it means one time field lines increases, another time field line decreases due to the movement of the bar magnet towards or away from the coil. It means some kind of variation of the field line occurs in the coil, and this variation of the field lines causes induced EMF and hence induced current in the coil. And due to the induced EMF or induced current in the coil, what happened? The galvanometer shows deflection. Basically, the induced current is very less in magnitude. So if you use ammeter instead of galvanometer, probably you are not going to get any kind of deflection. As galvanometer is sensitive, that's why a very small amount of current it can detect. So the deflection of the pointer of the galvanometer shows that there is an induced EMF and hence induced current, because there is no source connected across the coil. So as per the statement, the phenomenon of producing induced EMF and hence induced current in a electric or in a closed electric circuit due to the change in magnetic field or change in magnetic flux linked with the closed circuit is known as electromagnetic induction. I think you have understood this part, what is electromagnetic induction and how we can induces EMF and current by varying the field lines. Now next topic which we are going to discuss is your magnetic flux. So here is same as that of electric flux. So let me read out. Magnetic flux through any surface is defined as the total number of magnetic lines passing through that surface. So definitely a magnetic flux is not a number, rather it is a physical quantity with the dimension. But as per the definition what we have written, magnetic flux through any surface is defined as the total number of magnetic lines passing through that surface. It means magnetic flux is proportional to the number of field lines. More the field lines passing through the surface, more is the flux. So in this figure, we have considered a particular surface area which is normal along the direction of the area, and along the direction of the area we have projected field lines caused by the magnetic field B vector. Now in the first figure, area and the field is in same direction. It means the angle is 0 degree. But in this case, you see the area is normal to the surface, but the field line makes an angle theta with the area. So magnetic flux in this case, you have to define phi equal to product of the area and the component of the magnetic field along the direction of the area. So phi equal to A B cos theta. Flux is basically denoted by phi, and mathematically magnetic flux can be defined as the product of the area and the component of the magnetic field along the direction of the area, that is A B cos theta. So if you take the dot product, that is your B vector dot A vector. So flux is your phi equal to B vector dot A vector in case of magnetic field. Now the next topic, so that's why we have written here magnetic flux through any surface is the product of the area and the component of the magnetic field along the direction of the area. So SI unit of magnetic flux is your Weber, WEBER, and short you can write WB. And 1 way bar, as per the expression phi equal to B vector dot A vector. So B is your Tesla and A is your meter square. So 1 Weber equal to 1 Tesla 1 meter square. So regarding dimension, again we are going to use this expression considering theta equal to 0 degree as per the first figure. So it is your BA. So phi equal to BA, so B dimension and A dimension. B dimension you will get from the expression F equal to QVB. So F equal to QVB, so B equal to F by QV. So F dimension if you substitute, Q dimension if you substitute, and V dimension, V is your velocity and A is your area, then finally you will get this expression M1 L2 T minus 2 A minus 1. So this part you can check it out by yourself. Now the next topic which we are going to discuss is your Faraday's law. So there are two laws put forward by Faraday, and number one is your whenever magnetic flux linked with a coil changes and EMF is induced in it, this induced EMF lasts so long as the change in magnetic flux continues in the coil. So till the magnetic flux changes through the coil, the induced EMF will be there. Once it stops, no induced EMF will be there. So this is your first law. And the second law as given by Faraday, this is very important because coming topic based on the second law, the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linked with the coil. It means more the rate of change of magnetic flux linked with the coil, more is the induced EMF. That is induced EMF E proportional to d phi dt. D phi dt is your rate of change of magnetic flux. So this is your second law. Now next law is your Lenz's law. This is very important. Now you see, before coming to this law, let me read out first of all, I think it's better. The polarity of the induced EMF in a closed coil is such that it opposes the cause which produces it. So let me to repeat. The polarity of the induced EMF in a closed coil is such that it opposes the cause which produces it. It opposes the cause. This part is very important. Now how can we explain this one? Suppose you do have a coil and you do have a bar magnet and you are bringing the north pole of the bar magnet towards the coil. So what will happen? Flux link with the near face of the coil changes, and as a result an induced EMF will come. Now the direction of the induced EMF as per the Lenz's law is such that it opposes the vary cause. It means north pole is varying towards the coil. Sometimes it is moving towards and sometimes moving away. That's why there is a flux change, and as a result induced current. Now induced EMF, what it will do? It will oppose the flux change, and for that what are the things that induced EMF must have to do? Now you see, if you bring the north pole towards the coil, the near face of the coil develops induced current, and the direction of the induced current is your anti-clockwise. Now if the near face of the coil develops anti-clockwise current, so what face that one? Then that face is your north pole as per the symbol we have written. So anti-clockwise direction of current will be there. Now as anti-clockwise direction current is there near face of the coil, so what will happen? It will not let the north pole of the bar magnet towards the coil. So it opposes the bringing of the bar magnet, north pole of the bar magnet towards the coil, creating north pole at the near face. Now when you try to take off the north pole away from the coil, again the direction of the induced current in the near face of the coil changes. Now it is your south pole, or current flows in clockwise direction. So one time anti-clockwise, then it becomes north when the north pole moves towards the coil, and when you take the north pole away from the coil, direction of the current changes. Now it is clockwise, and for that face behaves, near face behaves as a south pole. So there is an attraction, and it will not let the bar magnet away from the coil. So somehow it tries to decrease the variation. Now variation decreases means no induced EMF or no induced current will be there. Now if you want to maintain induced EMF or induced current, what you have to do? You have to do work against the force of repulsion as well as force of attraction. So what you have to do? You have to waste certain amount of energy against this repulsive and attractive force to maintain the induced current or induced EMF. Now as per the conservation of energy, the energy which you are using to maintain the variation, that energy gets converted into electric energy. So sometime in exam it is asked how Lenz's law explain the conservation of energy. So please go through. This part is very important, and this chapter itself is very important in your exam, board exam basically. Please go through and try to find out your doubts, and more we'll discuss in our coming class. Thank you.